please give them a big App Promotion Summit App Engagement Zone welcome to the stage.
Thanks so much, James. I've now got that picture framed on my fireplace, so I can look at it all the time. No, just joking. David, are you sharing the slides already, or?
Whenever you are ready.
I am ready.
Great. Good, should be on full screen now.
Yep, I see it. So welcome to our little chat about A/B testing, and particularly about ABCDN testing is more what we're talking about. David, if you don't mind going to the next slide. I'm Natalie Fitch. I'm a senior CRM manager leading the retention and engagement team at Babbel, and I'm here with my colleague David.
Yes, I'm David. I'm leading the, let's say, product-facing pillar of data, covering data science, machine learning, and product analytics also at Babbel.
I think next slide. Yeah, thank you so much for filling in the poll that we sent along. I think when I looked at it, there are some answers for every for each of these answers about basically, yeah, which factor do you find most limiting when it comes to A/B testing in your channel? I do see that the most answers are there at the long-term effectiveness of winning variance, which is something that yeah, definitely hits me hard, making sure that what we scale to the full user base sort of stands the test of time. And these limiting factors are what we're going to focus on today in our presentation. So I'll kind of go through a bit of a use case. David, next slide, please. Okay, so I've been, Corona has me sort of watching some French films. So I've sort of broken down this presentation into sort of our few different sections. So part one, the problem. Next slide, please. Just a quick heads up, David and I are about to say some downright despicable things about traditional A/B testing methods, and we just want you to know that we don't really mean them. We love traditional A/B testing methods. We use them all the time. We just feel that this new method that we're going to present today can actually enhance your current testing regimen. So we find them to be two complementary methods, basically, and we'll go through in which scenarios these different methods should be used. So next slide, please. So around the end of last year, the end of 2019, we were sort of posed this big, massive question. So this massive opportunity question, how might we bring a learner back from a period of dormancy? So let's say that we have a whole group of learners, they haven't been active in our app. So it's not that they haven't been learning, they haven't been active at all. How do we bring them back? This is sort of a CRM manager's biggest question, right? And we started thinking through options, and we came up with a few hypotheses. So, okay, we could nudge them to complete a lesson, we could nudge them to review their vocabulary, we could nudge them to listen to a podcast. But then things started sort of spiraling out of control, as they often do with our backlog build out, right? So we had a few ideas of how we could actually build this out. Okay, we could use a cognitive load trigger. There's too much to choose from. Let's make it easy for you. We could look at social proof. Look, there are thousands of other learners doing this, or other options there. Then we thought, okay, which channel? Maybe we can optimize open rate by testing subject line. We can optimize click rate by testing banner image and copy and CTA color. And all of a sudden, you have 1,000 ideas for how you can bring learners back from dormancy. And you have to choose basically which one to A/B test. So next slide, please, David. So this here is, yeah, let's say that basically you've narrowed it down to a few options. So we've decided the hypothesis that we're going to focus on. Yeah, if you click one more time, that's fine. So the hypothesis that we're going to focus on is, okay, nudging learners to come back and listen to a podcast will bring them back from dormancy, okay? We think of two ways that we can actually build this out. We focus on value add, so this really helps with your active listening skills. We focus on variety. This gives you something new and fun to do. We want to test a couple of banner images, test a few subject lines, and next thing we know, next slide, please, we have 12 variants, right? And this is just coming from a single hypothesis from our backlog. Let's say, for example, we build out this multivariate test. We have 10,000 daily triggers into this test, for example. Yeah, we've got 12 variants in one control group, so that leads to 769 daily sends per variant. And for example, perhaps the control group is exhibiting a 5% conversion rate, and we're expecting a 5% uplift on that conversion rate by the winning variant. This leads us to 6 months worth of testing, a single multivariate test stemming from a single hypothesis in our massive backlog will take us 6 months to test. So this is really, we don't have a lot of time for A/B testing. Here's sort of an extreme example of where you could see something like that. Next slide, please. Even further, let's say that we do actually run this 6-month test. We have our 12 variants along this x-axis along with our control group. We have our conversion rate along the y-axis, and we see that our variant number 2 is our best performing. But that means that over these 6 months, all of these other variants which have been underperforming have actually been losing us 20 conversions per day about. Oh, do you mind going back, please?
Right.
Yeah, I guess you can read it, but yeah, over 6 months that comes out to about 3,600 conversions lost during this one test. Next slide, please. Of course, this is now our biggest question or our biggest answer that was put in the poll. Let's say that this is our winning variant. This is variant number 2. We have this lovely image of a woman listening to her podcast. She's really enjoying it. She's smiling. We see that the value add copy has been the best performing one. We have the subject line, which talks about how you can learn Spanish on the go with the podcast. We scale it to the full user base in January. And this is what happens to the conversion rate over time. This could be due to nudge fatigue. This could be due to new features being put into the app that are stickier than podcasts, for example. This could be due to different messages going out in our channels. So then sort of the marginal impact of each individual message goes down. So they kind of cannibalize each other. But actually in this case, our hypothesis would be that talking about learning Spanish on the go doesn't actually fit to the current world situation. So we're all living it right now, and none of us are on the go, or very few of us are on the go. So we see that actually the conversion rate of this variant decreases over time, for example. Next slide, please. So so these are all these sort of challenges that we're facing with this A/B test, and basically we're looking for a different approach. How can what should we do when we're faced with all 4 of these challenges? And I'll kind of hand it over then to David to give you the solution. Part 2, the solution.
Thanks, Natalie. Yeah, as you have already guessed from the title of the whole presentation, this kind of algorithmic framework, this mathematical idea that can be used as a solution for this situation is what's called multi-armed bandits. And I'm kind of the data algorithm math nerdy guy in this presentation. And in the next little bit short of 30 minutes or so, I want to introduce you to what the multi-armed bandit problem from a data science point of view is in the first place. I want to give you an idea of one specific algorithm for solving that problem, and I promise to do the whole thing without bothering you with jargon or any single equation. So I believe that a lot of important applied math can actually be explained intuitively. And at the end of the presentation, you can tell me whether I succeeded here. So my promise, no equations here, nothing scary. So let's give it a go. First of all, let's talk about this somewhat silly name, multi-armed bandit problem. What does that mean? Where does this come from? Now, even mathematicians like to use little stories here and then rather than equations to get a grasp on their problem. And this kind of intuitive story behind the equations of this problem is what gives it the name. So imagine you are a gambler and you enter a casino, you want to play slot machines, like the one depicted down here. Slot machines are sometimes called one-armed bandit because they, at least the old ones, used to have this lever on the side, and you would pull that and then the wheels spin, and depending on where the wheels get to stop, you would get some payout or not. So the lever is what makes it the one-armed bandit. The lever gives the arm. It's called a bandit, of course, because casinos calibrate them so you will lose them in the end. This is where the bandit comes from. Now, in our little story, we are imagining we're some kind of super gambler. So we're not just playing a single slot machine, we play a whole room of them, a whole bunch of them, and this is where the multi-armed comes from. So we imagine our slot machines are fairly simple. There's no sort of big win or small win. They're just win or lose. You get the same payout from each slot machine when you win. So we're not really looking at, hey, this one gives you $20 and the other one $10, or there's a jackpot. No, it's simply win or lose. All of them work this way. Each of the slot machines, however, and here comes the twist, has a different probability of winning. And this probability is not known to you as the gambler. So you enter this casino, you want to play, let's say, for a day. And what you want to do, of course, is you want to maximize your reward over time. You want to walk out with the biggest pile of cash you can get. Now, just intuitively, think for a second how you would approach this. I think it's fairly clear that if you actually knew the best slot machine, if you knew which machine had the highest probability of winning, then you could simply play that one for the whole day. This would be the optimal strategy because everything is random, sort of your mileage would still vary, but there's simply no better way of playing this than going for the best one and playing that all day. But you know, how would you actually find the best slot machine? You could say, okay, let's play 10 games on each. But you know, 10 games, it's not a lot. I think that's also intuition shared by all of us. You know, with 10 games, you could really be on kind of an unlikely winning streak on a slot machine that's actually pretty bad on the long run. Or you could be very unlucky, just lose a lot of times on one that would actually be pretty good in the long run. So, okay, 10 games, probably not enough. What about 100 games? Or let's be really safe. Let's play 1,000 games on each machine. But what do you do if after 50 games on each, we realize, hey, there's one that really looks much better than the others? Do we stick with our commitment to 1,000 games to be really sure, or should we rather bet on the one that looks really good after 50? Now, this kind of dilemma, this problem, this is called the exploration versus exploitation dilemma in the field. Exploration refers to the idea of gathering information about the slot machine to find out who the winner is, and exploitation means that we want to play the winner, the best one, based on the knowledge we already have to maximize our rewards. We can extend this story and add some complications. So let's say the casino manager spots us playing, you know, we're sort of a high roller, we play a lot, we leave a lot of money in the casino, and he decides, hey, we bring this guy 2 new slot machines every 30 minutes. What do we do then? We could even imagine, I guess this would be illegal wherever gambling is legal, but we could imagine that the probability of winning changes over time for these slot machines. What do we do in these situations? Now, this is just a story about gambling, but it's actually pretty straightforward to relate this back to the real world, to the actual problems you are facing in your business, or Natalie is facing with Babbel CRM. So all you have to do, you have to put in something for the slot machine that you're interested in, and you have to put the definition of winning that relates to your business. So your slot machine could be an online ad, and winning could be the click or the purchase following after the click or something like that. A slot machine could be an email. Winning could be opening, clicking, or for us in re-engagement, it is an activity in the product. Slot machine can be a creative variant. You can also have something much more complicated as a slot machine. So you can, for example, have, this is from my field now, from data science, you could play out different algorithms against one another. Which algorithm, let's say, of an online shopping recommendation system is the best one? All of these things can be approached in this framework. Now, what I've just described is the multi-armed bandit problem. So the term multi-armed bandit refers to the problem, and this problem is solved by a whole bunch of different algorithms. And we refer to them as bandit algorithms in the following. So the bandit algorithm is basically a computational strategy for solving this problem. Essentially, a set of rules of how the gambler should act in order to maximize their reward. Now, how many bandit algorithms are there? If you just go to Google Scholar and enter the term multi-armed bandit, you get around 31,000 results. And you know, this is not even web Google. This is just the Google that indexes academic research papers and books. So there are a lot of different bandit algorithms, and some of them are very, very involved and complicated. Some of them are very simple. Some of them are optimal for certain scenarios. Some of them are not. I talked about these little complications with the casino manager bringing in new slot machines over time, or with the probabilities changing over time. For each of these little versions and many more I have not addressed, there are different algorithms. Now, what I want to show you now is one specific algorithm that's called Thompson sampling. It's a very classic algorithm. It's surprisingly simple. It's very, very elegant, but it's not sort of dumbed down. It's a real actual bandit algorithm that is optimal under certain scenarios. And this is the one I'd like to at least intuitively explain to you now, so you get an idea of how this could work and how this works. If you want to implement this in practice, I would suggest you team up with your data science team in order to pick the right algorithm for the specific version of the problem you have, but it never hurts to know a little bit how these things work. Now, the Thompson sampling algorithm is based on something that I'm calling the magic curve here, because I promised to keep out the jargon. So to understand Thompson sampling, we must first understand this curve. And to do this, I have prepared a little interactive plotting demo. So I hope the screen has switched correctly, so you can see the magic curve now. Actually, I wanted to make this available to all of you. This has not worked out technically so far, because I need access to some kind of sharing system that's currently on preview. If you're interested, ping me. I guess the conference is sharing our contacts, so I can make this available in case you want to play around with yourself. So let's look at this magic curve. The magic curve takes two parameters to determine its shape. Firstly, the number of games played on a specific slot machine. So the magic curve is attached to each of these individual slot machines. The second parameter is the number of games we have won. So I can change these parameters here with these sliders. I'm expressing the number of games won with a fraction here, but in a way this doesn't matter. I could also just express it as the absolute numbers. So here we have 10 games played, and we have won 20% of them. And this is what the magic curve actually looks like. So the interesting question is, of course, how does the shape of the curve change when we play around with the parameters? You may already have observed that we have 20% of the games won, and the peak of this little mountain seems to be somewhere around 0.2, and that is not a coincidence. It's not exactly on 0.2, just in case you were wondering. So if we move around the fraction of games we have won, let's wait a little bit for the thing to update, you will actually see that we can move the peak of the curve. So now we're in 35% now, we can go to 50. So the peak of the curve is determined by the number of games we have won. And if we go all the way to the right, to the extreme, it's no longer a little mountain, it's more like a slope. But essentially, the number of games we have won changes the peak. Now, the interesting thing here, however, is the number of games we have played. Let's put the fraction of things we've won to 25%, but now increase the number of games we have played. And what happens here is that the mountain gets higher. You will see the absolute height on the y-axis here, and it also gets much narrower. So let's just look at two extremes. I'm going back to just 13 games played. The thing is super wide, and I'm going all the way up to something around 400, and this sort of nice wide mountain becomes this pretty narrow kind of spike. And also when it's narrow, I can move it around here by changing the fraction of games won. Now, what this curve represents is essentially our knowledge and our certainty about the real probability of winning on that slot machine, given what we have learned about it so far. So when we have very few games, the peak is very broad. It spans across a broad range of values on the x-axis. And you can see the x-axis as indicating the actual probability of winning on that slot machine. This is still unknown to us, but we know from this curve that certain values are more likely than others. And when we increase the number of games we played, the peak gets narrower and narrower, which means we are more and more certain that the real unknown probability lies in a smaller and smaller area. Just in case you're wondering about the math details, the y-axis is not probability. Probabilities are actually the area under the curve, but we don't really need to care about this to understand Thompson sampling. If anybody's interested in the jargon, where to look this thing up, if you haven't already spotted what it is, ask me in the Q&A section towards the end. Now, in order to do Thompson sampling, we need one more ingredient. This magic curve can also be used as a random number generator. And when I click here, show samples, it will just generate a bunch of random numbers. And as you can see, the shape of the curve determines where the random numbers will appear. So the higher the curve is, the more likely these little random samples are to appear in that specific area. So if I make the curve pretty broad, this field of random numbers gets broader and broader. When I move it around, the field of random number moves around. And keep in mind, all of this is random. So you can still get numbers where the curve is pretty low. Also, the curve actually never really is zero, although this is hard to convey in the graphic. And when we make the curve narrower, the field of random numbers gets narrower. So we know the magic curve, and we know that it can generate random numbers. And this is all we need to do and understand Thompson sampling. So let me go back to the slides here. Good. So now comes the actual Thompson sampling algorithm, and it's really simple and elegant. It's just 4 steps. We're doing it for 2 slot machines, for 2 bandits now, but this scales naturally to any amount you might want. So first step, for each of our bandits, for each of our slot machines, we compute the magic curves using the number of games played and the number of wins. So in our scenario here, we have two of them, which are named A and B. You see the curves are somewhat similar, but slightly different. B, it's a little bit broader. It's maybe a little bit more, well, hard to say. Both of them have something between 10 and 20% of wins. A little bit more games played on A. Why? Because the curve is a bit more narrow. So for each of our slot machines, we do a curve. Second step, from each of these curves, we pick a single random number, not a whole bunch as I did before, but really just a single random number. So for A, it's shown, where's my pointer here? It's shown down here in this axis. It's somewhere above 0.2. And for B, it's somewhere between 0.1 and 0.2. Third step, we compare all of these random numbers and we declare the slot machine the winner that has generated the highest random numbers. Again, this would scale to any number of slot machine you would have. Here we have clearly slot machine A as the winner. So the winner is the next slot machine we're going to play. So we pull the arm and we update our stats. What do I mean by update the stats? Well, we have played one more game in A and we have either won or lost it. And that's it. Repeat. So again, for each bandit, for each slot machine, and of course in the real world scenario, let's say for each ad, for each email variant, we compute the magic curve using the stats we have collected so far, number of games played, number of wins. From each of the curves, we pick a single random number and we play, next time we play the machine that has generated the highest random number. So very, very simple. But why on earth does this work? Why does this make any sense? Now, for this, I want to go back to my visualization and look at what the algorithm picks in different situations. So I'm not going into any proofs or equations here, but I think just looking at these curves, we can get some intuition on why this is a good idea. So this looks a little bit more complicated, so I'll walk you through it step by step. Here we have a two slot machine scenario. Again, you could do this for an arbitrary number of machines, but we want to keep it simple here in order to understand the visuals. So our slot machines are A and B, and both of them have, again, a slider for the number of games we played and the number or the fraction of games we've won. Now, for both of them, we're plotting the respective magic curves here. So the first one has the blue one, the second one has the orange one. I'm also plotting just a bunch of these random numbers here, so you can see roughly where they generate. But keep in mind, for the actual algorithm, we just pick one random number per curve. Now, on the right-hand side, I have repeated 1,000 times this picking of one random number per curve and looking at who the winner is. And then I've counted the winners and I've graphed them here in this little histogram. So in this specific situation, we have very few games played, 32 on A, 26 on B. We have a small difference in wins, 19% on A, 21% in B. So the curves have quite a big overlap. They're very, very similar. They're not identical, they're very similar, which means these random numbers generate in very, very similar space, which then means the one who's the winner, well, it's a bit of a tie. Sometimes the blue one wins, sometimes the orange one wins. And this is reflected here in this histogram. So in this situation, 2% difference, there is a difference between the two, but very little data. You could say that Thompson sampling will really bet on exploration. So very similar probabilities that either the blue or the orange one are played next. Now, let's play around with this a little bit. Let's say we get more and more success with the second machine. Now we look at scenario where we slightly increase the winnings here of B. Now we're 19 to 24, we have a 5% difference. you will see the curves move apart, the fields of these random numbers move apart, and the Bandit begins to bet more and more on machine B. It's still not too much data, but we slightly move from exploration towards exploitation. But you can see that the blue machine is still played around, well, 1/3 of the times. So this is really what we mean by balancing exploration, exploration and exploitation. So it's not sort of discarding one completely. It is still playing both a little bit, just in case to see whether something changes. Yeah, because we still don't have a lot of data in that scenario. So we still might be wrong to bet on B. And the more extreme we make the difference here, the clearer we are that the orange one is actually the better one. And the more you will see that the algorithm, that Thompson sampling, picks the orange one as the winner. Now, let's go back to our original situation. We had 19 and 21% here. So very balanced scenario, 2% difference only. Maybe go to 22. Let's see, what does that look like? Yeah, still very, very similar, 3% difference. But now let's look at a situation where we still have these 3% difference, but much, much more data. So we go all the way up to 500 data points here, 500 data points here. Now, again, we have the same small difference, but we have much, much more data. So we're much more certain that the difference between these two slot machines is real. And as you can see, the Thompson sampling will now clearly favor the one, although the difference was exactly the same as before. But now we have more data. We are more certain about the small difference, that the small difference actually materializes in the real probabilities, and we go heavily into exploiting B. And of course, if we increase the difference here, you will see that the probability of Thompson sampling picking version A goes down rapidly. It looks like we are at 0 here. Actually, none of these curves ever really touch 0. So there is always a little bit of a chance to pick a curve that looks worse. So Thompson sampling, like most of the Bandit algorithms, will never really completely stop exploring. Now, the last thing I want to explore here is the situation that we get this new slot machine, like we get something completely new in the pool. Let's say, yeah, Natalie's team has come up with a completely new email variant to test, or there's a completely new ad variant. How does that look? Let's say on B, we have still 500 data points, I don't know, 21% success rate. Now on the new one, we obviously have 0 data. So let's move this all the way to the left. So for 0 data points, the magic curve is just straight flat. Straight flat means the random numbers will show up all over the place, over the whole range of the x-axis, which means we have a fairly high chance of actually beating the random number from the orange curve, which means we have a fairly high chance that we will play Bandit A. So whenever something's completely new, whenever something new comes in the pool, Thompson sampling will start exploring that very, very aggressively. And now when the data comes in, so let's go back here to 0. So if we have something with 0 here, we're almost certain to pick that to generate then some data. As soon as data comes in, it really begins to depend on the quality of the thing. So we're here at 19% versus 21. So you will see that there is a preference for the orange one as we learn more and more about the blue one. But if the new one would actually be better, let's say, let's make this something like 27 or so, then very soon the algorithm will start to bet on the new version, and it does more and more so if we get more data. So Oh, sorry. That was not intended. Let me bring back my screen. Good. I wanted to go back to the slides rather than stop sharing. Yeah. So this concludes my hopefully intuitive exploration of the multi-arm bandit problem and one specific algorithm to solve it. And I'm handing back to Natalie.
Thank you. So part 3, the resolution. So how have we actually taken this particular approach and applied it at Babbel? If you don't mind going to the next slide, David, just as a reminder, at the very beginning or at the end of 2019, I would say this was our big question. How might we bring a learner back from a period of dormancy? Next slide, please. And we decided to go to sort of explore this bandit approach. It was a massive cross-functional effort, or it is currently a massive cross-functional effort, including the CRM and data teams, as well as product and engineering, content strategy, and learning experience design. We all have something that we bring to the table, and we couldn't do this project without any or missing any of those teams, basically. Next slide, please. This is, from a CRM perspective, kind of the technical flow of how this is working. So basically, on the data side, they've built out this algorithm, which we've seen, which chooses which email variant to bet on each time that we basically trigger an email. So that triggers, it allocates what we call variant IDs or template IDs to learners in this segment that we've predefined. Then it triggers a custom event for those learners, and it includes that variant ID in the payload of the event. For most of our variants, we're also pulling content from a content API. So all of that content is also pulled from that API, put in the payload of the event. And then that custom event that has all that payload data is triggered into our CRM tool. Then in our CRM tool, we have an automation built out, which is triggered by this event, and then learners are segmented based on that payload data. So that's how we're basically getting this, the decision that the Bandit is making about which email variant to bet on based on all other sends. That's how we're getting that data into the CRM tool and segmenting our users between the email templates, basically. Next slide, please. And this is kind of what it looks like for us so far. I would say we're early in the process. We don't have 1,000 variants going from our backlog. We have 20 at the moment. But when I think about what this would look like managing, if we were doing a sort of traditional AB or multivariate test here, I would be managing, or my team would be managing 140 emails. So we have 5 hypotheses, each with 4 creative variants in 7 different languages. It would be basically unmanageable. And so this is a really, really great approach. I think along the bottom, this sort of colorful bar, what you're seeing is basically the day that we turned the algorithm on. So we ran this for a long time without using the smart sort of Thompson sampling, basically, yeah, almost randomly allocating these variants in order to collect data. And then you see the exact day that it turned on, and it started favoring this yellow variant, which is a lesson recommendation coming from our recommendation API, and scaling back the other variants while still sending those variants to users to continue collecting data. So basically with the understanding that if this lesson recommendation basically stops working, or if we introduce a new variant that is more engaging for our learners to bring them back from dormancy, the Bandit, we call it the Bandit, will scale back that yellow variant that we see there, that lesson recommendation, and will scale up the new, more engaging variant on its own. Next slide, please. So if we think about a typical CRM workflow, we go from ideation all the way down to pushing it live, reporting, and ideating the next steps. And it's sort of a loop, right? It's a testing loop. And what's really great about this approach is that it is removing some of what I would consider some of the most daunting steps of this process. So the experiment setup and then all of the reporting are done automatically by the Bandit. And we're able to reallocate the time that we would typically spend on that to the most important parts for our learners. So that's the ideation and the creative development. So making sure that we're really getting the best content possible in front of our learners and spending our time on that instead of experiment setup and reporting. Next slide, please. And for us, this isn't the end. We're a big fan of this approach so far. Like I said, we're quite early in the sort of having it live and working with it. But some of the really cool things that we can use the Bandit for in the future, for example, is maximizing other values. So at the moment, we are maximizing, or what we consider our win for our slot machine is learning. So starting a lesson, starting a review, starting all of these learning activities, but we can also apply this to different values. We can apply it to revenue, we can apply it to lifetime value, which is really interesting. We can also apply it to more complicated values like learning durations. We want to increase the number of minutes or hours that our learners are learning. And we're also keen to sort of expand it to further channels and use cases. Next slide, please. We thought that these might be interesting questions. Sorry, I'm just checking the time. Oh, we're fine. We thought that these might be interesting questions here. So why why do we recommend that you build the Bandit in-house, and when should you use it? Basically, I think building the Bandit in-house definitely helps with the flexibility to optimize different outcomes. So this win, we have it currently as a minimal learning activity, but we can change that anytime because it's built in-house, right? So all we have to do is drop a Slack message. You know, sorry, David, I'm like oversimplifying this. Like, all we have to do is drop a Slack message and it's done. That's not the case, but yeah, it's all done in-house. So all these things about different like which segments different variants can go to and which outcomes we're optimizing for. For us, it's all very flexible because it's all built by a team in-house, which is really great. Also, I really like our data teams, and I highly recommend making friends with them if you're not friends with them. Yeah, and then I'll hand over to David for this last one. When should we use a Bandit?
Yeah, so Natalie touched upon we don't want to sort of trash talk A/B testing. So there's space for A/B testing and space for multi and Bandit approaches. And I think especially like in the field, you can have long and sometimes heated discussion on when, what, especially if you have more like machine learning people like myself discussing with more traditional statisticians. So when should you use a Bandit? I think one thing that's important to keep in mind, Bandits are primarily an automation tool. So they don't make your campaigns magically more effective, but they help you balance this exploration, exploitation, help you getting out of this A/B testing loop, and they help you sort of juggle a lot of different variants at the same time automatically. So when should you actually use them? Typical scenario is you have a large pool of small, fast-changing variants to optimize over. This is why it's so great for, let's say, emails, push messaging, ads or so. You wouldn't use Bandit in, let's say, traditional product A/B testing when you have sort of one big feature versus another one. That's still very much the A/B testing domain. But when you have a lot of small, fast-changing variants to optimize over, then it's an interesting thing to consider. Also, when you want to add new ideas, new variants frequently, this is also something that the Bandits can handle very nicely. And also when you expect for impacts to change over time. And all of these really apply to these kinds of ad, emailing, push messaging scenarios. Back to you, Natalie. Oh, back to the discussion.
Yeah, so we have a couple of questions. David, I can kind of moderate those if you'd like. I think they're better for you. So I see there's one, did you develop and implement the solution in-house, or is there any tool that can be used to tackle this issue? Actually, I can kind of hit on that one. Oh, am I still in the Zoom? Oh, good. Okay, there you are.
Yeah.
I was like, oh no.
Showing our faces now rather than the presentation.
Perfect. So we did hit on that we did develop this in-house, and also I would say David and I are not experts in, I would say marketing tool, the market for marketing tools. So I couldn't say if this exists elsewhere. I do know that some CRM tools have some similar approaches. They aren't quite as long-term as what we're looking at here. So really scaling and killing over a long period of time. But I know that, for example, Braze and Amarsis, and I think also Leanplum, but I couldn't say for certain, have something like this where they will watch maybe the first 20% of sends and see which open rate is higher, and then it will scale that open rate for the last 80% of sends, things like this. But it's not this sort of long-term adding variants and taking them out and thing that we're talking about here. David, do you have any other?
One more comment from my side on this one. So I've also seen tools also for, let's say, the domain of like front-end optimization, having versions of that. What was really the driver for us to build it in-house is that we can go very, very deep really in the product with the definition of what winning actually means. So we're not optimizing clicks or opening rates. We could do that, but we're not doing this. We're really optimizing behavior in the product further down the road. And this, I think, can get very, very challenging with out-of-the-box solution because of integration and things like that. It sounded nice and simple, but actually there's quite a lot of subtleties in these Bandit algorithms. So I, as leading data science and machine learning, feel much more comfortable having my data scientists read those papers and really think what is the algorithmic approach for our specific scenario, rather than leaving this to some purchased black box, because it can get subtle.
Cool. Cool. Yeah, we have a couple of more questions, but David, I just wanted to let you know that in the chat there are loads of compliments and little hearts and thumbs up to your demo. People really liked it. Great demo, really well explained. Thank you, bell curves for the win. Loads of really nice stuff in there, just in case you don't.
Thank you.
Okay, are you using this for social media advertising? At the moment, it's just in our CRM channel that we're using it, but I don't see why not. Why you couldn't. A similar approach. Yeah. But at the moment we're still sort of in this exploratory phase there, so that's why we're keeping it in a specific segment in a specific channel. But I could see us definitely scaling it other places. Any other thoughts on that, David?
No, I mean, as long as kind of the technical requirement as that you can automate, you can like remote control the tool, for in our case the CRM system. It has an API, we can remote control it, we can then attach our algorithm. So you need this kind of openness or API access to your tooling, but as soon as you have that and the capabilities in-house, you can do that.
Last question here, and I'll let you handle it all on your own, David. Do you set some sort of time limit until you calculate a win or a loss?
Yeah, that's a tricky one. So we have defined our definition of winning is that the user has a specific kind of activity, namely a learning activity, within 7 days after receiving the email. And this delay is not great for the algorithm. So one of the complications is sort of how to do bandits when the reward is delayed. And think of an e-commerce scenario or so where people really are looking at months or week before people might purchase. And this significantly complicates the math. So we're still using a simple algorithm with our 7-day window. Yeah, we are debating whether, hey, should we maybe go down to 3? But for us, it's part of the definition of what a win is. Just keep in mind, if this window gets very, very long, you might want to look at a different version of the algorithms. But in a way, it's something you can play around with. So you can set this as part of your definition of what winning means. But we are debating whether 7 is a good idea or whether we might go down to 3. I would say from an algorithm's perspective, the more immediate it is, the simpler it gets. So using Thompson sampling, actually we do something slightly more complicated, but a version of Thompson sampling, let's put it like this. So Thompson sampling with 7 days is still kind of okay-ish. But yeah, something that's immediate is always easier for the algorithm. So a pure, let's say, open or click optimization is definitely easier from an algorithm perspective.
Thank you so much. Another interpretation of this question that I had, so I'll address it just in case that's what you meant, Leon, is that if we put, for example, 20 variants in there and we see that one is performing much better than all of the other 19, do we ever kill those 19? This is something that we haven't done before, but we've talked about it. But the whole idea of the system is that you still sort of have some faith that there is value in these other 19 variants, and that at some point they may become this favored variant amongst learners. So I think the idea, correct me if I'm wrong, David, is that you kind of never kill something unless it's particularly bad or out of date or something like this.
Yeah, I think in a way, yes. I think the biggest problem you get from having lots of stuff in there is that the graphs you use for reporting gets very, very messy. I mean, you saw Natalie's little rainbow graph, and eventually if the pool is just huge, you might want to reduce it just to keep sort of your reporting digestible for the human brain. The algorithms in a way don't care, but yeah, just to keep the reports clean, it's probably a good idea to kick out stuff that really hasn't been bet on for a long time. And of course, whenever you think, hey, shouldn't we come back to that idea, you could put it back in the pool and have it tested.
Mm-hmm. One last really interesting question from Johannes is, are you using bandits for more complicated business KPIs like spending or number of conversions rather than conversion yes or no? So at the moment we're saying either yes, they did a learning or no, they didn't. But if you're thinking about something like maximizing revenue, for example, David, do you want to hit on that at all? We're not
using it, especially Thompson sampling and sort of variants of it really rely on this, coin toss, win or lose, yes or no scenario. But there certainly are algorithms where the rewards can be arbitrary numbers. This is part of these 31,000 hits on Google Scholar. You will find that there. It does complicate your math though.
Hi guys, I'm gonna, just to keep us on time, I'd love to continue discussion, and it's great. Yeah, we've had so many good questions and comments. What I suggest is, could you guys maybe drop into the chat now, if you've got time, and pick up any sort of last questions, and maybe David, you can share your contact for the tool, or maybe sort of drop in there is probably the best thing. And yeah, David, you just need to add in your email to the swap card thing, and hopefully Natalie can sort of get you on there. And yeah, I'm
not really sure how to access that.
Okay, great. Well, maybe hopefully we can get you on there, and yeah, great. All right. Well, really appreciate you guys taking part today, and it was great to do something, a bit more kind of deeper and it would sort of thing would work very well in one of our workshops. And it also worked really well today online. So really appreciate you putting so much work and thought into it. And I know, you know, there's a lot of appreciation out there in the audience too. So just want to say a big thank you.
Thanks for having us.
Thanks.
Great. Thanks, guys. All right.